6.3 Lesson 1, Logistic Differential Equation. Our objective here is to use the logistic equation to model a problem. Vocabulary, carrying capacity. So carrying capacity is represented by L. It's the same in both the logistic differential equation and the logistic equation. So here we have the logistic differential equation, and here we have the logistic equation. The logistic differential equation tells us the rate at which the population is changing with respect to time, and the logistic equation tells us what the population is at a particular time. So we saw how we get the logistic equation from the logistic differential equation by solving the logistic differential equation using separation of variables. The logistic equation is the general solution of the logistic differential equation, and the constants are K and B. And in a particular problem, you need to use given initial conditions to find the values of the constants B and K, and when you do that, you're finding what we call the particular solution of the logistic differential equation, satisfying the given initial conditions. Some things to note about the logistic differential equation is that K is positive, and it is the same value here as it is in the logistic equation for K. And when the population Y is less than the carrying capacity, Y divided by L will be less than 1, so the factor 1 minus Y over L will be positive, and the rate of change of the population will be positive, which means the population will be growing when the population is less than the carrying capacity. And that makes sense, because the population will continue to increase as long as it is below the carrying capacity. But if for some reason the population should be greater than the carrying capacity, then Y over L will be greater than 1, and this factor 1 minus Y over L will be negative, and dy dt will be negative, which means the population will be decreasing. So whenever you have the population greater than the carrying capacity, the population will be decreasing. Whenever you have population less than the carrying capacity, the population will be increasing. So other things to note are, again, as I said already, K is the same in both equations, and L is the same in both equations. One thing to note is that the logistic differential equation tells you the rate of change of the population with respect to time, but on the right side of the equation there is no variable for t. So that's one thing to note. And the logistic equation tells you the population as a function of time, and you do have t on the right side of the equation. So now let's look at an example for using the logistic equation to model a problem. Before we do that, let's just quickly sketch what the graph of the logistic equation would look like. So you have a horizontal asymptote for the carrying capacity, and as time goes on, the population will approach the carrying capacity, and the logistic curve would look like that. As you will see in one of the recorded lessons, the population is growing most rapidly when the population is at L over 2, or at half of the carrying capacity. So at this point, you can see that the logistic curve is steepest, meaning that the population is growing most rapidly when it is at half of the carrying capacity. So here we're looking at example 10. A state game commission releases 40 elk into a game refuge. So this is at time is equal to 0. At the time of release, there are 40 elk. So if you're already starting to organize information, you have ordered pairs ty, where t is the time in years, and y is the population of elk. So the first sentence says the state game commission releases 40 elk into a game refuge. So at the time of release, we will say time is 0. After 5 years, the elk population is 104. the Commission believes that the environment can support no more than 4,000 elk. That is called the carrying capacity, the limit of the elk population that is sustainable. The Commission believes that the environment can support no more than 4,000 elk. So that is L. The growth rate of the elk population P is given by this logistic differential equation when the population is between 40 and 4,000, where T represents the number of years. Write a model for the elk population in terms of T. In other words, write the logistic equation. This is the logistic differential equation. We want to write the logistic equation. Of course, you don't need to solve the logistic differential equation using separation of variables. We've already looked at that, but you do need to remember the general solution of the logistic differential equation, which is called the logistic equation, and we're going to use these given initial conditions to find the values of the constants B and K in the logistic equation. Here we're using the variable P to represent the population, and it really doesn't matter. You can have P represent the population, or you can have Y represent the population, but wherever you have Y, you just have P, and if that's the case, you will just have P here instead of Y as well. But that's not a big issue. I can just simply change all the Y's to P's, and it'll be consistent with how we're labeling here. So I should probably change this to P as well. So P here. So I have dP dt is equal to K times P times 1 minus P over L, and here I have P is equal to L over 1 plus B times e to the negative kt. Now we already know what L is, so I can replace L here with 4,000. I can also replace L here with 4,000, but we don't really need to worry about the logistic. Well, it's already here. That's already been given, so we already have that. So whatever K is here, it'll be the same K that we have in the logistic differential equation. But how can we find K? How can we find B? We can find K and B by using these initial conditions. So I will substitute 0 for T and 40 for the population, and when I do that, I will get 40 is equal to 4,000 over 1 plus B times e to the negative K times 0. So e to the 0 is 1, so I have 40 is equal to 4,000 over 1 plus B times 1, or 1 plus B. Multiply both sides of this equation by 1 plus B, and I get 1 plus B times 40 is equal to 4,000. Divide both sides of the equation by 40, and I get 100. So B is equal to 99. So I know B is 99. So the other constant that I need to solve for from the logistic equation would be K. And once I have B and K, I will have what we call the particular solution of the logistic differential equation satisfying these two initial conditions. What we have here is the logistic equation, which is the general solution. So let's go ahead and replace the B with 99, and we will solve for K. So we have 1 plus 99 times e to the negative kt. To solve for K, we'll use the other given information that when time is 5, the population is 104. So we will go ahead and substitute 104 for the population, and we will substitute 5 for T. So e to the negative K times T, or negative 5T. And now we have to negative 5K, because I'm substituting 5 for T, and I'm solving for K here. So it should not be negative 5T, it should be negative 5K. because I'm substituting 5 for t and I want to solve for k. So how do I do that? So this is some review of algebra, so let's go ahead and take a look. You're going to multiply both sides of this equation here by the denominator of the right side, and when you do that, you will get 104 times 1 plus 99 times e to the negative 5k is equal to 4,000. So we're trying to get k by itself. So we have to go one step at a time. The next step is to divide both sides of this equation by 104. So when you do that, this is what we have. So we have now 1 plus 99 times e to the negative 5k is equal to 4,000 divided by 104. The next step is to subtract 1 from both sides of the equation. That would give 99 times e to the negative 5k is equal to 4,000 over 104 minus 1, which you can write as 104 over 104. And 4,000 minus 104 would be 3,896. So you will have 3,896. And then you have to divide both sides of this equation by 99. So dividing by 99 is the same as multiplying by 1 over 99. So when you do that, you'll just have times 99 in the denominator on the right side. And on the left side, you'll just have e to the negative 5k. And then you will take the natural log of both sides of the equation. On the left side of the equation, when you take natural log, you'll have negative 5k. And on the right side of the equation, you'll have the natural log of 3,896 over 104 times 99. And the last thing that you need to do is divide both sides of this equation by negative 5 to get k by itself. And dividing by negative 5 is the same as multiplying by negative 1/5. So this is what k is equal to. And of course, you're going to use your scientific calculator or graphing calculator to get a decimal approximation, and you should find that k is approximately equal to 0.194. And I recommend that you don't round. You have maybe like a few more digits here just to avoid rounding error from your model. But let me go ahead and just write what our model is. So we have k is approximately, so I have negative 0.194 to the t power. That is our model. So write a model for the elk population in terms of t. We have it. And one thing to note is this k, it would be applicable for the logistic differential equation as well. Part B of the problem is asking something about a slope field, so we won't do that today. We'll be looking at slope fields later. But let's look at parts C and D. So again, what did we find for part A? For part A, we found the logistic equation that models our population of elk. So we will use P instead of Y. So we have the carrying capacity is 4,000 divided by 1 plus, we found B to be 99. 99 times e to the negative kt, and we found k to be about 0.194, so e to the negative kt would be e to the negative 0.194 t. So this is our model for the elk population as a function of time, where time is measured in years. So now we will use that to do part C. Use the model to estimate the elk population after 15 years. So that's really easy. You just substitute 15 for t. You're going to use your calculator and evaluate the right side of the equation when t is 15. And when you do that, you should find that the population 15 years later is about 626 elk. All right, so now we have the population 15 years later is approximately 626 elk. So now we look at part D, find the limit of the model as time approaches infinity. Now this is something for you to understand, and if you understand populations that are modeled by logistic differential equation and the logistic equation, then it's actually something that you will know right away, because the carrying capacity of the population is 4,000. So we know that the population starts below 4,000. So what happens as time goes to infinity? The population will just approach 4,000. So find the limit of the model as t approaches infinity. The limit of the model as t approaches infinity is 4,000. The population will approach the carrying capacity. Now I can show that algebraically, and here's how I can show it analytically, and here's how I would show it. So we want to know what happens as t goes to infinity. So we want to take the limit of the logistic equation as t goes to infinity. So here's our logistic equation, 4,000 over 1 plus 99 times e to the negative 0.194t. So when you take the limit of this logistic equation as t goes to infinity, how would you do that? Well, you can work with this exponential expression in the denominator, and what you will see is that because the exponent is negative, you can do the following. You can write 99, and you can take the power, which has a negative exponent, and write that in the denominator with a positive exponent. And of course, as t goes to infinity, this expression, this exponential expression, will also go to infinity. As t goes to infinity, e to the 0.194t will go to infinity, which means 99 divided by e to the 0.194t will go to 0, which means the denominator will approach 1, which means the quotient 4,000 divided by the denominator will approach 4,000. So that's how you get that the limit is 4,000 as t approaches infinity, again reinforcing what we mean by the carrying capacity. So today we were able to use the logistic equation to model a problem. We looked at vocabulary such as carrying capacity. This is called the logistic differential equation, telling us the rate of change of a population with respect to time, and the general solution of the logistic differential equation is called the logistic equation. And here's how the graph of a logistic equation would look like. There is a horizontal asymptote at y is equal to L, the carrying capacity.